Example 1. A solid cylindrical aluminium conductor has 25 km long and the area of the conductor is 336,400 circular mils. Obtain the conductor resistance at 20 degrees Celsius and 50 degrees Celsius. The resistivity of aluminium at 20 degrees Celsius is ρ is equal to 2.8 times 10 to the power of minus 8 ohm meter. So let's say we have a conductor. Here, this aluminum conductor has resistivity equal to 2.8 times 10 to the power of minus 8 ohm meter. And the length of the conductor here is 25 kilometer and the area is 336,400 circular mils. Okay, so from here, if we use the SI unit, we need to change this unit to meter square. So we know that 1 cmil is equal to 5.067 times 10 minus 4 millimeter square, or 5.067 times 10 minus 6 centimeter square, or equivalent to 5.067 times 10 minus 10 meter square. Okay, so to calculate the resistance, the DC resistance at 20 degrees Celsius, we know that the formula is ρ multiply with the length of the conductor divided by the area of the conductor. And from here we know that at 20 degrees Celsius the resistivity of the aluminium conductor is 2.8 times 10 minus 8 ohm meter multiply with the length of the conductor, which is 25 kilometer, divide by the area, which is 336,400 cmil. We change to meter square, so we need to multiply with 5.067 times 10 to the power of minus 10 meter square. So if you calculate, you will get the DC resistance is equal to 4.107 ohm. This is the answer for A. The answer for B, at 50 degrees Celsius, RDC, the DC resistance at 50 degrees Celsius is equal to the DC resistance at 20 degrees Celsius, which is RDC at T1, multiply with T plus T2, which is the temperature that we need to find, divide by T plus T1. So RDC at T1 is 4.107 ohm. The temperature constant, this is the temperature constant, this temperature constant for aluminium conductor is equal to 228 degrees Celsius. So put the value here, 228 plus T2, which is 50, over 228 plus 20, which is the temperature at 20 degrees Celsius. And we obtain the DC resistance at 50 degrees Celsius is slightly higher compared to DC resistance at 20 degrees Celsius, which is 4.6038 ohm. So we can see that the temperature of the conductor is affecting the resistance of the conductor. Example 2. A transmission line cable consists of 12 identical strands of aluminium, each 3 mm in diameter. The resistivity of the aluminium strand at 20 degrees Celsius is 2.8 times 10 to the power of minus 8 ohm meter. Find the 50 degrees Celsius AC resistance per kilometer of the cable. Assume the skin effect correction factor is 1.02 at 50 degrees Celsius. So in this case, if we draw the conductor here, this aluminium conductor has, we assume the length of the conductor is 1 kilometer because we need to find the AC resistance per kilometer. Okay, and inside here, this conductor has 12 identical strands. So it has 12 strands. So each strand has diameter of the strand is 3 mm and it is identical for the total of 12 strands. So we know that the DC resistance RDC at 20 degrees Celsius is equal to rho multiply with the length of the conductor divided by the area of the conductor. And because the area here, we have 12 strands, so we need to find the area of the conductor, which is, we know that area is equal to pi divided by 4 times diameter square. So we can put all the values here. So diameter is equal to 3 mm. So we get the area here. Because we have 12 strands, so we need to multiply with 12 strands to obtain the area of the conductor. So multiply with 12 strands, we get here the area of the conductor is equal to 84.823 millimeter square. And if we put this value into the formula, so the DC resistance at 20 degrees Celsius is equal to 2.8 times 10 to the power of minus 8 ohm meter multiply with 1 kilometer divide by the area, which is 84.823 mm square. So we get here the DC resistance at 20 degrees Celsius is 0.33 ohm. And to get the DC resistance at 50 degrees Celsius, the formula is RDC at 20 degrees Celsius multiply with the temperature constant plus T2 over the temperature constant plus T1. So the DC resistance here is 0.33. The temperature constant is 228. T2 here is 50 degrees Celsius. Divide by 228 plus 20 degrees Celsius. So we get the DC resistance is 0.37 ohm, which is slightly higher compared to the DC resistance at 20 degrees Celsius. But the question asked for the AC resistance, and the skin effect correction factor is 1.02. So skin effect factor is equal to RAC over RDC, and this is equal to 1.02. So straightforward, actually we can find the RAC at 50 degrees Celsius. This is also at 50 degrees Celsius. So RAC at 50 degrees Celsius is equal to 1.02 multiply with 0.37 ohm. So we get the AC resistance at 50 degrees Celsius due to the skin effect is 0.3773 ohm.